Roberts. Ian Roberts is a Canadian who has moved to Leiden Observatory. Let's see, let me get his bio up here. Ian was born and raised in Nova Scotia, completed his PhD in 2020 from McMaster University, and is now a postdoctoral fellow at Leiden Observatory. His research interests cover various aspects of galaxy evolution across multiple wavelengths, with a focus on the impact of galaxy cluster environment on star formation. Speaking of McMaster University, I would like to begin by acknowledging that our speaker was educated on the traditional territories of the Mississauga and Haudenosaunee nations within the lands protected by the Dish with One Spoon Wampum Agreement. And Ian will be talking to us today about RAM pressure stripping in nearby groups and clusters, a low frequency perspective. I'm very excited to hear this talk, and Dr. Roberts, why don't you take it away?
Sounds good.
Deporting thousands of residents from Mariupol, taking them to Russia, where Ukraine says they could be held as hostages.
Okay. So yeah, hi everyone. I'm happy to sort of virtually be back with some Canadians, and looking forward to talking about some recent work that I've been doing over the last couple of years. Yeah, as was mentioned, this is going to cover RAM pressure stripping in nearby groups and clusters, but from a low frequency perspective based on the work that I've been doing here in Leiden with LOFAR. So kind of a fake radio astronomer, but I've been working with plenty of real radio astronomers who keep me in check, and I'm slowly getting the hang of this stuff. But yeah, today I'm going to be talking about galaxies like the one you see here on the title slide with these RAM pressure stripped radio tails, and how we can use wide area surveys to learn more about these types of objects. So this is my outline that I'm going to try and get through for the talk. I'll just start with a quick introduction into environmental quenching, RAM pressure, things like that. I'll talk a little bit about LOFAR, because I think that probably not everyone will be familiar with this telescope necessarily. And then a little bit on what we can learn from spectral index measurements in the radio continuum of these jellyfish type of galaxies, and I'll have more to say about exactly what I mean by a jellyfish galaxy in a few slides. I'm going to talk about how RAM pressure can potentially enhance star formation. It's not just a way to shut off star formation in galaxies. And then we'll see, if I have some time at the end, I also have a couple slides on molecular gas, if we can get to it. So I'm going to start here with the Coma cluster. This is what you see here in this image. Coma is one of the nearest massive clusters to us. It's been sort of the site of lots of research into galaxy evolution and the impact of galaxy clusters. And you can already start to see that impact just by looking visually at an image like this, not just Coma, really any galaxy cluster in the low redshift universe. You'll quite quickly notice that they are dominated by red elliptical galaxies, which are passively evolving. They're not really forming many new stars. You can look closely and you can probably find a few blue spiral galaxies in this image, but there's not too many, and they're kind of hard to pick out. See this maybe even more clearly if we zoom right into the center of Coma, and basically everything you see in this image is an elliptical galaxy that is red and dead. So it's clear just by looking at these pictures that galaxy clusters have a pretty profound impact on the star formation activity of member galaxies. So this is not what we would see if we looked at isolated galaxies or galaxies in low mass groups. So we'd see a lot more ongoing star formation. Just to show this a little bit more quantitatively, so in this plot, I'm showing the star formation rate of individual galaxies on the y-axis versus stellar mass. So the mass of the galaxy in stars. You can see this upper sort of trend between star formation rate and stellar mass. This is what's known as the star forming main sequence. This is where normal star forming galaxies tend to live. So the grayscale in the background of this 2D histogram is showing this distribution for isolated galaxies. So in the grayscale, those are galaxies that aren't part of a cluster, aren't part of a massive group. And it might be a little tricky to see with the points overlaid, but you can take my word that the majority of these isolated galaxies are on the star-forming main sequence. These are actively star-forming galaxies. The points I've overlaid in blue and red, these are now member galaxies of the Coma cluster. So the blue points are star-forming galaxies in the Coma cluster, and the red points are passive or quenched galaxies in the Coma cluster. And the quenched population, you know, is much more populated in Coma relative to isolated galaxies in this plot. So this is this environmental quenching that I'm talking about. And this is not just true.
Dr. Roberts?
Yeah.
I apologize for interrupting, but you have a little bit of a blockage in your upper right corner. William pointed it out. If you wouldn't mind moving that. Thank you. Perfect.
There we go.
Okay, perfect.
No problem.
Thank you so much.
So this isn't just true for Coma. This is pretty generally true of galaxy clusters. So this was first noticed, you know, back in the 70s, 80s. So on the left-hand plot here, this is a famous plot from Alan Dressler in 1980, the so-called morphology density relation. So the y-axis is just showing fraction of galaxy type over a population. And the x-axis is some measure of galaxy density. So this is basically a projected number density of galaxies. These different lines are corresponding to different types of galaxies. So the open circles are elliptical galaxies, the filled circles. Let me see here, it's a little difficult to make out the points. The filled circles here, these are S0 or lenticular type galaxies. And these X's are spiral and irregular type galaxies. So the takeaway here is that as a fraction of the total population in low density environments, on the left-hand side of this plot, you're dominated by late type galaxies. And in high density environments, you're dominated by these early type galaxies, ellipticals, and S0s. So this is exactly what we find today with much larger samples, thanks to surveys like the Sloan Digital Sky Survey and many others. This is sort of an updated version of the morphology density relation from Willman in 2012, and it's the exact same picture. The only difference is on the x-axis here, instead of doing a projected number density of galaxies, it's being plotted directly as a function of halo mass. So massive clusters around 10 to the 14, 10 to the 15 solar masses are on the far right-hand side of this plot. And towards the left, you move through massive groups down to low mass groups, sort of local group analogs. So it's pretty well established now that these environmental trends, in particular with respect to galaxy star formation or galaxy morphology type, they're clearly there observationally. So within the field, the shift has sort of come more to trying to understand physically why these trends are there. So what are driving these trends that we see observationally? What physical mechanisms, which must be specific to dense environments like groups and clusters, are shutting off star formation in these galaxies. So this is a favorite cartoon of, I think, many people who work in this area. This was put together by Ari Chung, and it's highlighting some of the different physical processes which have been put forward in the literature to try and explain this phenomenon. So some of these processes are dynamical, sort of gravitational interactions between galaxies. Some of these processes are hydrodynamic in nature, basically interactions between the galaxy and the intracluster medium. I'm not going to step through these one by one, but I'm just going to focus on what the bulk of my talk is going to focus on, and that's the process of ram pressure stripping. So the way that this works is as the galaxy is orbiting through a galaxy cluster, it encounters the intracluster medium. So that's sort of denoted by the kind of salmon color here. And the relative velocity between the galaxy and the intracluster medium drives this ram pressure, which can strip gas out of the disk of the galaxy. So the ISM here is represented in blue, and you see this tail or this wake of stripped gas being left behind the galaxy. And in particular, if you can pinpoint the direction of this tail or the direction of this wake, if you observe it, this is telling you something about the motion of the galaxy within the cluster as well. It's giving you, to first order, the direction of motion, of course, modulo things like projection effects and orbital uncertainties, which are an unfortunate observational reality. So I think I have, yeah, just to give you there we go. A quick video, which was made by ICRAR in Australia, which I quite like, just to show this in action, a bit of an animation. So this is sort of what we're hoping to see observationally. What we're hoping to catch is these galaxies forming these tails of material that's being left behind. And as this cold gas is stripped out of these galaxies, in turn, the star formation will shut off. And so if we want to understand this process further, we want to understand, how common this process is in galaxy clusters and galaxy groups. We need to build up we need to be able to catch this in action. Basically, we want to try and observe galaxies which have these tails, which have these strip features, and so that we can, catch this process while it's happening. So what do we look for observationally? This is where these jellyfish galaxies come into play. So this is sort of the idea here with the jellyfish galaxy. So classically or historically, these jellyfish galaxies were originally, this phrase was used for these galaxies which show these strip tails, these tails of strip material, but more specifically, they show signs of active star formation in these strip tails. So these are the sort of blue images here. This is rest frame optical and UV. In the lower left here, this is H alpha from MUSE. But in any case, these are all clear examples of compact star forming regions. So there's clear evidence in these cases that not only is there material being stripped off of these galaxies, but there really is active star formation going on in these tails. So that originally is what was meant by this phrase jellyfish galaxies. It's since sort of broadened within the community to mean any star forming galaxy which shows evidence for a ram pressure strip tail at some wavelength. So this could be these sort of classical jellyfish galaxies. It could also be star forming galaxies that have tails in the radio continuum, which I'm going to talk about a lot throughout this talk, dating back to the 80s. Atomic hydrogen, this is from VIVA, a survey of the Virgo cluster with the VLA. Or X-rays as well. So this is Chandra X-ray emission. And so these tails are really multi-wavelength objects. And I'm going to use this sort of broader definition of a jellyfish galaxy throughout the talk, just to mean any star-forming galaxy which has one of these one-sided tails in a group or a cluster. So I talked a little bit about why it's important that we can identify these objects. But so how do we do this? How do you try and select samples of galaxies that are being affected by ram pressure stripping? I'd argue there's kind of two main approaches you can take. You can do very targeted observations of well-known cases. So there are a number of galaxies in the low redshift universe, which are sort of prototypical in some sense examples of, or extreme examples of ram pressure stripping. They're known objects. They've been observed in a lot of detail at many, many different wavelengths. So this is really targeting specific galaxies that a priori, either through some older observations or some other way. And this is an object which has a tail, which is undergoing ram pressure stripping. You can do really detailed analysis of this. And this gives you lots of information on that specific object, but you can't really draw conclusions about the larger population this way. You end up with really pure samples, but also quite small samples. And you, like is often the case in observational astronomy, you tend to be biased towards the biggest, brightest, most spectacular examples, because those are the ones that get telescope time. So another approach, I would argue, is to try and, instead of observe individual galaxies, try and observe or survey entire galaxy clusters, or even samples of entire galaxy clusters, and then look at all of the galaxies in those systems and try and find the ones that you think are experiencing ram pressure stripping. So this will give you larger samples. You are looking through a much, much larger sample of galaxies, but you're probably going to sacrifice purity. You need to be, doing some type of observation where you can actually identify whether that galaxy is undergoing ram pressure stripping or not. So in terms of surveying entire galaxy clusters, this would most often be done through some sort of wide field optical imaging, for example. And then you could try and look at the optical morphology of galaxies and say, I think this is a galaxy that's undergoing ram pressure stripping. But unless you have one of these sort of classical jellyfish galaxies where you very clearly see knotty star formation in the tail, which is not that common, then it's much more ambiguous. You might see a warped disk, you might see sort of a tail-like feature, but it's hard to say for sure whether this is ram pressure stripping. I've done this myself, and I've looked at a lot of galaxy images, and it's hard to know for sure. You can put forward, candidate objects, but it's hard to be conclusive. That's it. If you do have a way to do this where you can survey entire clusters, you're going to end up with a more representative sample, because you're going to be looking at all of the galaxies in that cluster, not just the most spectacular ones. So this is where I'm going to talk about LOFAR, because I'm going to argue that LOFAR, in doing these radio continuum observations, in particular at low frequencies, is a way to kind of bridge the gap between these two approaches. So to do really wide area search that covers entire clusters, but also to probe a component of the galaxy which is actually readily affected by ram pressure stripping, as opposed to, for example, the stellar disk, which is quite resistant to ram pressure stripping. So LOFAR. LOFAR is an interferometer, the low frequency array. It is basically, there are two components to the LOFAR telescope. There is the Dutch stations, which are distributed throughout the Netherlands. So on the left-hand image here, I'm showing you one example. This is what's called a superterp in the Netherlands. This is a collection of actually 6 LOFAR stations. So the these sort of metallic objects on the ground there kind of look like the CBC logo. It's nice to have an audience that will get that reference. Those are antennas for LOFAR. Those are antennas from the quote unquote high frequency band in LOFAR, which is at 144 megahertz. So this is still very low frequency, and this is about a factor of 10, for example, below the L band, the 1.4 gigahertz of the VLA. If you look really closely, you can see sort of smaller kind of square rectangular patches in this image as well. Those are antennas for the low frequency band of LOFAR, which goes down, which has a sort of midpoint frequency of about 50 megahertz. So I'll also mention that there are a number of LOFAR stations which are distributed outside of the Netherlands throughout Europe. And so these are known as the international stations, which all form what's often called the International LOFAR Telescope. These international stations greatly increase the baselines for your interferometer, and therefore you can achieve much higher resolution. I'm just mentioning this for anyone that's interested. Everything I talk about today is going to just be with data from the Dutch stations. So if you just use the Dutch stations within the Netherlands, with the high band antenna, or the HBA, at 150 megahertz, you can achieve about 6 arcsecond resolution, which is really unprecedented for these frequencies. With the LBA, so the lower frequency band, with the Dutch stations, you can get to about 15 arcsecond resolution. With the HBA, with the 150 megahertz band, if you fold in the international stations, this is very non-trivial to do. There are a lot of people in Leiden right now who are working hard on developing the software and the computing resources to process the data from the international stations as well. But if you can do that, and there has been some success, there's been some papers coming out over the last year in particular, you can actually get down to 0.5, 0.3 arcsecond resolution at 150 megahertz. And the other thing I'll mention is that with the HBA, for example, the primary beam, so basically roughly the field of view of the telescope, is about 4 degrees full width half max. So you're achieving 6 arcsecond resolution, but over a field of view that's many square degrees. So this is one of the things that makes LOFAR so valuable as a survey instrument, and you can really cover a huge fraction of the sky in a relatively reasonable amount of time, and do surveys across, for what I'm interested in, across many different groups and clusters. So I'll also mention that the LOFAR 2-meter sky survey, so this is a survey with the HBA band at 150 megahertz from LOFAR. It will eventually image the entire northern extragalactic sky. It's about 60 or 70% complete now, I think. And I'll just mention that the second data release of this survey was just made public earlier in 2022. There's a paper by Tim Shimwell. I certainly recommend you check it out if you're interested in this type of data. Oops, sorry about that. So yeah, over on the right-hand side here, the sort of green and pink and white is showing you what parts of the sky have been observed by LOTS, by this 2-meter sky survey. The yellow region, this was the data release 1, and the black region here, both the 12-hour field and the 0-hour field, is the data release 2. So there's now more than 5,500 square degrees of this imaging, as well as visibilities, which are all publicly available. I just have some example images of a radio galaxy and shocks and relics in a galaxy cluster here that you can get from the LOTS survey. So it's really this data that I've used to do this search for these jellyfish galaxies in low redshift groups and clusters. And it's this extremely wide area that has made this possible. So can we detect these ram pressure tails with LOTS? So they should be resolved, at least at low redshift with 6 arcsecond resolution, in particular if they are long tails. And this has been done previously, so I showed it an image earlier, but ram pressure tails have been detected in the radio continuum. This has previously mostly been done at 1.4 gigahertz, just because that's where the VLA has observed. And so there's some images on the right-hand side. These are 3 galaxies, 3 jellyfish galaxies in the Coma cluster. These images were published a couple years ago by Chen et al. And this is VLA 1.4 gigahertz continuum imaging. And you can see these tails extending asymmetrically about the galaxy center, which is marked with the cross there. So LOFAR is actually, in some sense, even better for finding these objects because there's pretty good evidence coming out over the last few years that these strip tails in jellyfish galaxies, sort of like strip tails in other types of radio galaxies, probably have steep spectral indices, and I'll have more to say about exactly what that means in a few slides, but basically that means that they should be comparatively brighter at lower frequency. So as you move to lower and lower frequency, the tails should get brighter and brighter and brighter. So if you can see them at 1.4 gigahertz, you certainly should be able to see them at 144 megahertz. And combining the HBA and the LBA from LOFAR, we should actually be able to test this and measure spectral indices in these types of objects that we're finding. And then the advantage of LOTS, I've already talked about the wide area. Also, the uniform data is an important one too. So the survey is observing roughly to uniform sensitivity all across the sky. So we're not, biased in terms of, some clusters or some fields being observed to higher depth than others. And there's also, just based on the area that I showed on the previous slide, there's fantastic overlap with things like the SDSS spectroscopic surveys. So we have excellent redshifts and things like that for these galaxies. So basically what I've done is used all of this LOTS imaging from LOFAR and to look for these jellyfish galaxies in nearby groups and clusters. So this work was published in a couple of papers last year. We surveyed about 30 low redshift galaxy clusters, so redshift below 0.05, and hundreds of galaxy groups. So basically what we did is we just took all of the spectroscopic members of these systems, and then we made optical plus LOFAR 150 megahertz overlay images like I'm showing on the right. These are 4 galaxies in the Coma cluster. You have an optical image in the background, and then the contours that I've overlaid are the 150 megahertz emission from LOFAR. So, and then we just visually identified objects, star-forming galaxies, which have these one-sided radio tails. And so this amounted to about 100 of these jellyfish galaxies in clusters and 60 in lower mass galaxy groups, the vast majority of which are new detections. So some, in particular in clusters like Coma, had been previously identified as jellyfish galaxies from other wavelengths, but the vast majority of these objects are new detections. So I just want to point out a couple science highlights from these sort of first two survey papers. Just what we can do now that we have a bit more of a sample size here. So we have 150 galaxies or so. We can start to look at things in a little bit more of a statistical fashion. And so one thing we're finding, and this is confirming previous work by others as well, is that many of these jellyfish galaxies and clusters are showing actually enhanced star formation rates. So I tease this in my abstract. But what I'm showing here is the offset from the star forming main sequence. So back in the introduction, I showed the star formation rate versus stellar mass plot, and we had the star forming main sequence along the top of that panel. So this is just taking the vertical offset from that main sequence. So galaxies which are above this dashed line, so have offsets above 0. These are galaxies which, for their stellar mass, have larger star formation rates than the average isolated galaxy in the field. And the same converse for below this dashed line. So the lots jellyfish galaxies I'm showing here in red, they're comfortably above this dashed line. So this is evidence that these have enhanced star formation rates relative to field galaxies. I will make the point that we do have a selection bias here as well. So the low frequency radio emission that we're measuring from these galaxies, this is also a reasonably good tracer of star formation rates. So this is where the cosmic rays that we're seeing through synchrotron emission, this is where they're coming from. They're being accelerated by supernova explosions. So we are in some sense biased in that it's going to be easier to detect galaxies with low FAR that have high star formation rates. So to kind of gauge the effect of this, I'm also showing this gold line. And this is the line for galaxies which are also in these clusters, which are also detected in lots. So they're also bright at 150 megahertz, but they do not have tails. So these are not jellyfish galaxies. And so these galaxies are also above the main sequence. So this is the selection bias that I'm talking about. But even then, the lots jellyfish galaxies are still higher than we would expect from these sort of more standard cluster galaxies. So similarly, now that we have a sample of these types of galaxies, not only in high mass clusters, but also in galaxy groups going all the way down to 10 to the 13 in terms of halo mass and below, we can try and look at the frequency of these types of galaxies as a function of environment. And so that's what I'm plotting here on the left is the fraction of the jellyfish galaxies. And this is a fraction of the total number of star-forming galaxies in these groups and clusters as a function of halo mass. So low mass groups on the left-hand side of this plot and massive clusters like Coma on the far right. And so what we find is this pretty clear trend with halo mass, where these jellyfish galaxies are most common in massive clusters. This is what you would expect naively. Ram pressure scales with the density of the intracluster medium. So we have a dense ICM in clusters. It's going to lead to stronger ram pressure. Also scales with the relative velocity between the galaxy and the intracluster medium. So where you have higher velocity dispersions in clusters, this is also going to lead to stronger ram pressure. And then this steadily declines as you move to lower mass systems. This is, again, not necessarily surprising, but this is the first time that this has been shown clearly observationally like this. And this is this sort of type of population analysis we can start to do if we build up larger and larger samples of these types of objects. Okay, so now I am going to move on and talk a little bit about a spectral index, what the spectral index is in the context of these low frequency radio observations, and what it can tell us about potentially star formation in the disks of these galaxies, but also the history of stripping for these tails that we see. Okay, so just a brief aside on the radio SED for star-forming galaxies. I'm showing the SED at radio frequencies for M82, which is a nearby starburst galaxy on the right. So this is really a combination of dust emission, which is at the high frequency end, so sort of above 100 gigahertz, free emission, this is coming from H2 regions and generally is brightest between 10 and 100 gigahertz, at least brightest relative to these other components. And then at the low frequency end, below 10 gigahertz or so, you start to become dominated by synchrotron emission. So this is what we are seeing with LOFAR, basically exclusively. So interestingly, all three of these components are tracers of star formation rate, just in slightly different ways. And the spectral index is essentially just the slope of this SED in the synchrotron regime. So synchrotron emission is typically modeled as a power law. So we can see this sort of magenta dashed line is the synchrotron component of this fit. And the slope of this line is what we would call the spectral index. So it's just a ratio in the sort of this direct way of calculating it between your flux density at two frequencies and then just the ratio of those frequencies themselves. So rough values you would expect for this spectral index. So after injection from star formation, so from supernova, you typically get a value of minus 0.7 or so. And then if you have what is often referred to as a steep spectrum source, this spectral index steepens to -1 or even more negative. And this is what I was talking about earlier when I said that LOFAR and these low frequencies are best for finding these types of tails, because you win a lot in terms of flux density as you move to lower and lower frequencies, especially if you have an object that has a steep spectrum. So in a related sense, while the synchrotron spectrum may initially be a power law, and this is how it's modeled, over time, this won't necessarily remain the case. So that's what I'm showing on the right here. This dashed line, you can think of as sort of your initial spectrum for just a population of cosmic rays that are giving off synchrotron emission. But over time, if just left alone, the shape of the spectrum will change, in particular, just due to the dependence of the radiative timescale on frequency. You end up losing high frequency emission first, and then progressively this spectrum sort of cuts off at the high frequency end and steepens over time. So as you move later and later in time, you end up with a steeper and steeper spectral index. This also induces some curvature into your spectrum, which if you have enough frequencies, you can measure that and there's information in it, but yeah, you need 3, 4, 5 frequency measurements to actually constrain that curvature well. But even with just two data points, you will certainly see that over time, again, we're assuming that these cosmic rays are not being reaccelerated in any type of way, that your synchrotron spectral index is going to get steeper. So why is this important? Well, if we imagine a scenario in our jellyfish galaxies where these cosmic rays are being accelerated within the disk of the galaxy, just due to star formation, they're then being stripped off of the disk via ram pressure. If that's sort of all that's happening, then we should see that as we move further and further along the tail, the spectral index should get steeper and steeper and steeper. We should see a gradient from the galaxy to the end of the tail. That said, as I showed earlier, some of these jellyfish galaxies have active star formation going on within the strip tails. And that active star formation can be a source of newly accelerated cosmic ray electrons. They can reaccelerate the electrons that were stripped off of the galaxy potentially. And this could basically disrupt this gradient. So you could end up with a much flatter gradient or perhaps not even a gradient along the tail. If you have ongoing star formation in the tail, there are also other things like turbulence in the intracluster medium could potentially reaccelerate these electrons as well. So by testing whether you see this gradient along the tail, this is telling you a little bit about the history of stripping in your galaxy, and maybe is a useful way to try and determine whether you have ongoing star formation in the tail or not. So that's what we are trying to do currently. This is work in progress. What I'm showing are let's start over here. So the LOFAR images, so at 150 megahertz, for these are two galaxies in Coma cluster, NGC 4848 and NGC 4858. So in the blue, this is the LOFAR 150 megahertz. In the red here, this is the VLA imaging from this Chen 2020 paper that I mentioned earlier. And then I'm combining these two frequency images to make a spectral index map of the galaxy and also of the strip tail. So you can see the tail is clearly longer in the LOFAR imaging. So this is, again, because of the steep spectral index. And in particular for NGC 4848, we see this nice gradient along the tail. So you can see this also on the left here, where I'm just plotting, this is just spectral index on the y-axis versus distance along the tail. I'm just taking slices progressively along the tail. So for NGC 4848, we just get progressively steeper along the tail. This is consistent with a scenario where you're not getting significant reacceleration as these cosmic rays are stripped out of the galaxy. I'll also note that the spectral index is actually flattest on what I'm going to call the leading side of the galaxy. So if you look at the image again, the cross marks the optical center of the galaxy, but the spectral index actually is flattest on the opposite side of the center of the galaxy. So opposite to the tail. I'm going to call this part of the galaxy the leading side as opposed to the trailing side, and I'm going to use the terminology quite a bit throughout the rest of the talk. This is probably because we're getting enhanced star formation being induced sort of right on this leading edge where the galaxy is encountering the intracluster medium, and I'm going to have a lot more to say about that over the second part of my talk. I will just briefly mention that for NGC 4858, so for below here, while there's still a gradient with the distance along the tail, there is maybe, this is marginal, and as I said, work in progress, some leveling off of this gradient and maybe even a really small bump in the spectral index. I'm only mentioning this, so I'm highlighting this in red. I only mention this because NGC 4858 is a galaxy in coma that's well known to have active star formation going on in its strip tail. So this is an HST image of NGC 4858, and you can see these clear signatures of star formation in the F350 from HST. And this is the same region that is marked in red on that radial profile to the left. So it's possible that this is a signature of this ongoing star formation, and that this is potentially a viable way to find jellyfish galaxies with ongoing star formation in their tail to look for these sort of bumps in the spectral index profile. But still work needs to be done to confirm this. In particular, we're going to try and add in a couple more frequencies from the UGMRT to try and make a more complete picture here. So before I move on, I'll do sort of a brief aside on this nearby galaxy, NGC 2276. This is still related to the spectral index stuff. This is a nearby galaxy. It's a member of a sparse galaxy group, only about 5 known members. And this is one of, it might be the earliest example of ram pressure stripping in a group galaxy. As this dates back to the 90s. It's very inconveniently located for observations. It's basically plus 90 almost in declination. But this is an beautiful HST image on the right, and you can see this is, even just from the optical morphology, this is a disturbed looking galaxy. It's asymmetric. We get bright star formation on this side, which, as you will see in the next couple slides, this is this leading side of the galaxy, which is opposite to the strip tail. These are the original sort of tail images for this object, published in the 90s and in 2006 by Rasmussen. So this is an early VLA image at 1.4 gigahertz above, and then ROSAT X-ray image. So you can see, evidence for a very modest tail in this galaxy. And because of this, I just was curious, and this object happens to be observed by LOFAR. And so I wanted to see what it looks like in LOFAR, and this is what we see in LOFAR. So the top two panels, this is NGC 2276 at the HBA, and then the LBA. This is my first LBA image I'm showing. So this is at 54 megahertz, even lower frequencies. We see this spectacular tail, which is 60, 70 kiloparsecs longer than what was previously known from ROSAT or from the VLA. And because this galaxy is so nearby, we're reaching, with HBA and LOFAR, we're reaching basically kiloparsec resolution. So this is going to be, again, this is work in progress, but this is going to be a really interesting object to dive into further. And this, I have a feeling, will be the sort of the best ram pressure tail that we get from LOFAR. I'd be surprised if we got something that looks better than the HBA image here. I have the spectral index profile again in these lower images, the spectral index map on the left, and then again, radial profile, just taking slices along the tail. Again, I'll note the spectral index is flattest not at the center of the galaxy, which would be 0 here, but on the leading edge, again, probably due to this high star formation that's going on there. And then maybe we have this bump in the spectral index profile. Maybe this is star formation. This is this part of the tail here. The LBA image is still quite noisy. So we have to do a little more work to see if we believe that this is real. But we also are going to try and get H alpha imaging of this whole tail. As that would be a way to, look for or rule out the presence of star formation going on in this tail and whether it coincides with this feature we see in the spectral index profile or not. Okay, so speaking of star formation, I've already mentioned this a couple times, but this idea that we can get actually enhanced star formation, in particular along the leading edge of these jellyfish galaxies due to ram pressure. And physically, this is probably gas in the interstellar medium, which is being compressed as the galaxy, flies through the ICM in a cluster group. You're getting compression in the ISM, which is leading to high star formation on the leading side of the galaxy. So I'm going to show examples of a few different ways that we can constrain this possibility in a resolved way. In a Perseus cluster, which I'm going to talk about now. Also, I'm going to have some slides in 1 or 2 slides on some galaxies in the Coma cluster as well. And then a broader survey with some CFHT imaging. But let's talk about the Perseus cluster first. So earlier this year, we published actually the first detection of jellyfish galaxies in the Perseus cluster. Perseus is kind of funny. It's been studied a ton at sort of X-ray and radio wavelengths, but there hasn't been a lot of work actually on Perseus from a galaxy evolution perspective. Part of that is because it's relatively close to the disk of the Milky Way, so you have some extinction issues. But we found 4 jellyfish galaxies within the central R500 or so of Perseus. I just have 3 on my slide here. Subaru image on the left here. And then again, LOFAR HBA, so 150 megahertz images on the right, and we see these strip tails. So there is also, this is a mix of archival as well as some newly obtained narrowband H alpha imaging from the Isaac Newton telescope in La Palma to try and resolve the star formation pattern within these galaxies. So these are the H alpha images, continuum subtracted for these 4 jellyfish galaxies I'm showing here on the left. And then we've identified basically compact H alpha sources using the Astrodendro code, which was developed in Canada, and Eric Rosolewski's his group. So this basically decomposes these images into a dendrogram, sort of like a tree structure, and then basically we're taking the leaves, so to speak, of this dendrogram as these compact H alpha sources. So it's just a hierarchical way of identifying sources and images. And so what we find, you can see this even visually, is that in particular in UGC 2665 here, as well as UGC 2654 below, we have this arc of H alpha sources, which are along the leading edge of the galaxy. So I'm showing the direction of the strip tail with the orange sort of yellow arrows in these images. And then on the right, a little more quantitatively, this is the surface brightness of these individual sources, which we've identified versus their orientation with respect to the direction of the tail. So basically, we're just taking the relative angle between each of these sources and this observed tail direction. So 180 degrees would be sources directly on the leading side, so they're 180 degrees away from the strip tail. And then 0 degrees would be sources which are directly in line with the tail direction. And we see this trend where the surface brightness of these sources in H alpha increases as you sort of move to the leading edge of these galaxies. So I'm also, again, this is sort of work in progress, but using data from Union's consortium here in Canada as well. In particular, the U-band component from CFIS. So this is CFHT U-band imaging, which has a lot of overlap with the LOTS DR2 area. So the LOTS is in green here, and the CFIS U-band imaging is in blue. This footprint is probably somewhat out of date for the CFIS imaging. But in doing so, a lot of the jellyfish galaxies that we've identified are covered by this Union's imaging. And so we can use the U-band imaging to resolve star formation within these galaxies. And again, look on the leading side of these galaxies using the direction of the LOFAR tails relative to the rest of the galaxies. So again, I've just kind of had a look at this, a quick look, but what I'm showing here are, let's see, 6 of our jellyfish galaxies here. And the left-hand column is the CFIS U images, and then the right-hand column is the LOFAR image. The red box sort of roughly corresponds to the field of view that I'm showing in the CFIS images. In many of these galaxies, we again, if you look especially relative to the tail direction on the right, we see this bright U-band emission, so bright star formation, preferentially being found on the leading side. And again, 50, 100 of our jellyfish galaxies are covered by this imaging, so we'll be able to, not just study the galaxies that sort of show this enhanced star formation along the leading edge, but also test how common this is. What fraction of our jellyfish galaxies show this? What fraction of them just show sort of relatively symmetric star-forming disks like you would see in the field? And then I also wanted to mention some work, again, on this topic of resolving and mapping out where this enhanced star formation is happening in these types of galaxies. This is work that was done by a master's student that I've been working with here in Leiden, Maujin. So it turns out that about 20 or 30 of our LOTS jellyfish galaxies have been observed by MANGA. So they have integral field spectroscopy. So we can use this to map the spatial distribution of star formation, stellar mass, various emission lines across these galaxies, across the disk of these galaxies. The MANGA field of view, unfortunately, doesn't cover the tail regions. These are primarily within COMA and ABAL 2199. Both these clusters have a lot of MANGA observations. And so on the right, what Maujin has plotted is he's split the galaxy into, again, 2 sides. So he's divided the galaxy in half relative to the tail direction. So he's made a leading side of the galaxy and a mask to select the trailing side of the galaxy on the side of the tail. And he's just measured the star formation rate for MANGA on the leading side compared to the trailing side, and done the same on the x-axis for the stellar mass. And then this is just the difference between the two. So for the y-axis galaxies, which are above the 0 line, these are galaxies which have enhanced star formation on the leading side, so on the side opposite to the strip tail. And then similarly for stellar mass on the x-axis. So what Maujin's finding is that almost all of our jellyfish galaxies, which are covered by MANGA, have more star formation going on this leading side. But this is not the case for their stellar mass maps. And this is, again, sort of what you would expect from ram pressure. You don't expect ram pressure to induce a huge difference in the stellar mass distribution of these galaxies. So we still see relatively symmetric stellar mass distributions, but you expect it to have a much stronger effect on star formation and ionized gas and things like that. And just
So
to give
Robert,
you,
we're approaching time, so 5 more minutes.
yeah, it should be good.
All right, fantastic.
And then just a visual, I'll show you what this looks like in some of these galaxies. These are for, again, coma jellyfish galaxies. The arrows are showing the direction of the tail from LOFAR, and then I'm showing the H-alpha map from MANGA. We can see, in particular for these two on the left, this very spectacular difference between the leading side of the galaxy and the trailing side of the galaxy in terms of H-alpha emission and star formation. Okay, I will take 1 or 2 minutes to say something about molecular gas. This is going to be in the context of Vertigo primarily. So this is an ALMA large program, which is led by Toby Brown at NRC. I'm part of the collaboration. In particular, I'm interested in the galaxies covered by Vertigo, which maps CO emission in about 50 Virgo galaxies, a subset of which have strip tails, which are visible in H1 from the VIVA survey. So I'm particularly interested in these tailed galaxies, which are covered by Vertigo, to try and probe the distribution of CO and molecular gas in these galaxies. So in particular, are we seeing enhanced molecular gas densities on this leading edge like we might expect from this picture that I've been talking about? And I'll just jump to this plot quickly. And this is showing for 8 of these tailed galaxies in Vertigo. So this is one example on the left, NGC 4654. What I've done here is just taken surface brightness profiles, again, along the leading side of the galaxy and along the trailing side of the galaxy, measuring the CO surface brightness. The red lines here are going in the direction of the leading side, and then the black lines are going in the direction of the trailing side. And so we can see in some, not all, in about half of these galaxies, we get enhanced CO surface brightnesses along the leading side. And down below in the lower right here is just showing the average surface brightness along the leading side versus the trailing side, and then taking the ratio. So galaxies in the upper part of this plot have denser CO or denser molecular gas on the leading side. And so again, about half are consistent with sort of equal, and about half show enhancements. And we're still working with a relatively small number of galaxies, but yeah, hopefully over time we can start to build up more and more molecular gas observations of these types of galaxies. And so with that, I am a couple minutes over, so I'll just leave my sort of takeaways up here. I think I've already talked about these all, and yeah, I'm happy to take any questions from the audience.
All right, thank you so much, Dr. Roberts.